let's look at the MGF of the sample mean. Okay. Now my samples x1 through xn are IIDx and my x is centralized Bernoulli half. Okay. So that's why my moment generating function became e power lambda by 2 plus e power minus lambda by 2. So x is centralized Bernoulli half. Okay. So that's the distribution for the x. Okay. Now what is my sample mean? It's going to be x bar, which is x1 plus dot 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 plus xn divided by n. Okay. So far we never saw the divided by n. Okay. So far we just looked at x1 plus xn. We never concerned ourselves with this division by n. Now this division by n is very, very critical. Now what I'm going to do is I'm going to write this as simply x1 by n plus x2 by n plus dot 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 xn by n. Okay. Now what is this? This is, what is x by n? Okay, what is x by n? Now this x is centralized Bernoulli, so x is minus half half with probability half half. Okay, x by n is actually minus 1 by 2n and 1 by 2n with probability half half. It gets shrunk, right? So if you think of x as being minus half half with probability half half, as n increases this comes down and down. So it becomes minus 1 by 2n, 1 by 2n. The probability half half remains the same. Probability equals half, this is probability. That remains the same at half, but as you increase n, it keeps coming down and down and down. So each of these guys, right? So if you look at the sequence x1 by n, x2 by n, so on till xn by n, these are IID according to x by n. Okay. So that's the story here. Okay. Now all I need to do is find the moment generating function for x by n. Okay. And then from there I can go to the moment generating function of x bar, simply raising it to the power n. Okay. That's what has happened here. Okay. So the moment generating function for x by n is e power 1 by n lambda plus e power minus lambda by 2n divided by 2. Okay. So it's half into, so this is basically half into e power lambda into minus 1 by 2n plus half into e power lambda into 1 by 2n. It takes value 1 by 2n with probability half, minus 1 by 2n with probability half. This is just just addition and writing it up. So once you find mx by n, what is the moment generating function for x bar? It is just the IID sum. IID sum of x by n distribution. So it is just this moment generating function raised to the power n, e power lambda by 2n plus e power minus lambda by 2n by 2 raised to the power n. Remember, this is just a function of lambda. Okay, so there is just one variable here. N is just like a parameter, so it is just a function of lambda. Okay, keep that in mind. Okay, so we are able to find the MGF of sample mean for the case of centralized Bernoulli quite easily, and we write it down. You get an expression like that. So now what you can do is you can plot. Okay, so here is a plot for the MGF of the sample mean mx bar of lambda was as a function of lambda for different n. Okay, so you can see what is going on here. It's really, really interesting. I'm starting with n equals 1. I get a big cup like this. So notice the y-axis here. It's around 1. Okay, 0.9997 to 1.0004. It's very close to 1. I've just zoomed up the area around 1. Okay, that's what I've done here. And then I plot for n equals 10. Notice what's going on here. It's just sort of shrunk down. And then for n equals 20, 50, 100. And notice what's going on. As you keep increasing n, we observe at least visually, okay, even though we have not proved this analytically, we won't prove it. You can prove it if you like to, but it's if it keeps coming down, it becomes flat. And it's a fact that this mx bar of lambda will tend to 1 as n increases, as n goes to infinity. Okay, so this should not be surprising to you. Why should this not be surprising to you? Because we already know from the weak law of large numbers there is some sort of a conversion for x bar, a convergence for x bar towards the expected value. What is the expected value of x? It's centralized Bernoulli half, of course, is 0. So I know x bar is somehow converging to 0. And what is the MGF of the constant 0? It should be the flat function 1. Okay, so this MGF is actually converging to the flat function 1, which is the expected value of x. Okay, so it's not very surprising, but look at this very nice picture that you can draw with this. Okay, What I'm going to do next is one very subtle and very profound change to what I've done here. Okay, so the one thing that is crucial is this division by n. Okay, and I got this division by n and then raised it to the power n, and I got this wonderful convergence to something flat. What if I change n? Okay, so this is a very profound and subtle question. What if I change n? Instead of dividing by n, what if I divide by something else? What is that something else? Why is that crucial? All that is a little bit deep and a little bit involved. Maybe I'll point you to something interesting later on that. But let's try it. Let's see what happens in the same case. If we divide, instead of n, we divide with root n. Okay. So you can ask me, where is the root n coming from? Why is it well motivated and all that? Maybe I'll give you some pointers to why the root n becomes important here. But it's crucial. This root n scaling instead of 1 by n scaling changes things fundamentally and in a very, very interesting way. Okay. So the setting is same as before. I have IID samples according to centralized Bernoulli. Expected value of x is 0, variance of x is 1 by 4. Note that down. The variance will not change when you translate, right? It's just 1 by 4. Now, previously I considered x1 plus xn divided by n. That was the sample mean. Now, I'm going to consider this other scaling, which is division by root n instead of n. Once again, you may ask, why root n? What is so special about it? You will see the result is really special when root n comes in. Okay, you'll see why that's really, really special. But it's a bit profound and very interesting that root n causes this kind of a fundamental change in what happens to the MGF. Now, I mean, technically the derivation, there's nothing different. Whether I divide by n or root n, it's the same thing, right? Instead of x, I will look at the moment generating function for x by root n. So instead of 1 by 2n, minus 1 by 2n, I'll have 1 by 2 root n minus 1 by 2 root n. Nothing changes there. And so the moment generating function for y is simply this e power lambda by 2 root n plus e power minus lambda by 2 root n by 2 raised to the power n. So all these mechanics, there's no change, and you can use Desmos or something. You can easily generate this and plot. Okay, so that's what I've done here. Notice the profound change. Okay, look at the huge change here. Okay, so I want you to, I'll walk you through how I've plotted it. This my I've plotted for different values of n. First is n equals 1. Okay, so you see for n equals 1, it will just be the e power lambda by 2 plus e power minus lambda by 2. I told you how it looks. No, it looks like e power lambda squared. Okay, it will look like this. This e power lambda square will look like this u, right? So it's sort of like this e power lambda square. Okay, notice what happens as you keep increasing. So I've put a t here. I apologize for that. It should be lambda e power minus lambda squared by 4 by 8. Okay, it's not minus also. Okay, so this is wrong. So let me just this should just be lambda e power lambda squared by 4 8. Okay. So I have the blue line for n equals 1, that is sort of like that. And then notice what happens when n becomes equal to 10, and then when n becomes equal to 20, it is not converging to something flat, it's converging to something that looks like e power lambda squared, some e power lambda squared by 8 or something. In fact, you can see that e power lambda squared by 8 is exact, and if you do a little bit of work here, you can show that this will converge to e power lambda square sigma squared by 2 as n increases. And what is sigma squared? This guy is sigma squared. Okay, sigma squared is 1 by 4. Okay, so you see e power lambda squared by 8. That's what this converges to, e power lambda squared by 8. Okay, so this is nothing short of magic, it turns out. So you may say it's one special case for if you put n, you're getting a flat 1. Now you put root n, you're getting this e power lambda square sigma square by 2. So what is so nice about the e power lambda square sigma square by 2? This MGF corresponds to normal 0 sigma squared. Okay, notice this wonderful little property. The centralized Bernoulli, you add it up n times, divide by root n, you get the normal distribution. Okay, that's what happens. As n increases, you're going to get a normal distribution. Okay, so fantastic little result. So the binomial can be close to a normal distribution in some sense. Okay, so this is sort of the root of central limit theorem and how it works. Okay, now you might argue, okay, so this is for the binomial distribution, centralized binomial. Maybe for only the binomial distribution this is true. Turns out that's where the real wonder of the CLT comes. The real speciality of the CLT comes because you can take some other distribution. Okay, so I have picked here one of the other distributions we saw before, and looked at the same thing. We repeat the same thing, okay? Nothing has changed here. I've taken n IID samples here. Instead of that simple mx of lambda, now I have a more complicated mx by lambda, which has a certain expected value and has a certain variance, phi by 2. Now this is the sigma squared here, no? Okay. Oh, here again I've made this mistake here. So it's not minus, it's plus 5 lambda squared by 4. Okay. Apologies for that. Okay. So this is the distribution. It's a different distribution. It's not centralized by Bernoulli anymore. It's some other complicated distribution. But I define the same scaling. Okay, y is x1 plus so on till xn by root n. So now I have to do mx by root n and then raise it to the power n. I get this funky looking formula. So right, some complicated e power lambda by root n sort of and then raise it to the power m. Okay, and here you go. I've plotted this for n equals 1. It looks very out of shape, no, asymmetrical plot which looks a bit different, but as you keep increasing your n, but this time looks like I have to go to a larger and larger n, okay, so that's okay, n equals 100, n equals 200, it has an asymmetric form, lot of values, but by the time I go to n equals 200, I can start seeing some convergence, right? So you look at the convergence, it's actually converging to, once again, e power lambda square sigma squared by 2, e power 5 lambda squared by 4, which is again e power lambda squared sigma squared by 2, and from our formula, the formula that we mugged up, right, you remember I asked you to mug up something by heart, this is the MGF of normal 0 sigma squared. Look at that amazing little result. What did we do? We went from n to root n, okay, instead of dividing by n, we divided by root n, and the distribution in some sense converges to a normal distribution, and it doesn't seem to matter what the initial distribution is. Whatever the initial distribution is, it seems to be converging to normal. Now it turns out this is an astonishing, surprising fact about IID samples. Okay, whatever the distribution is, if you take IID samples, and that's the central limit theorem, the celebrated central limit theorem, okay, if you take IID samples according to some distribution x, let's say expected value of x is 0, once again I told you that's not a serious limitation, you can simply subtract, and variance is sigma squared, and then you do this scaling, y equals x1 plus xn by root n. It can be any distribution, it doesn't matter, these two conditions have to be satisfied. Then this MGF my of lambda, as you keep increasing n, will tend towards e power lambda squared sigma squared by 2. Okay, and this is the MGF of the normal distribution. This kind of a property is called convergence in distribution. So you say your y converges to the normal distribution in this fashion. Okay, so this is a celebrated theorem. Look at the astonishing fact here. It doesn't matter what the distribution of x is. Okay, you take IID samples, divide by root and add them up and divide by root, and notice that subtle change. If you divide by n, what happens? You remember the previous result I showed. If you divide by n by the weak law of large numbers, the MGF will go to 1. Okay, it converges to 1. But if you divide by root n, you don't go so aggressive on the division, you go by root n is smaller than n, right? Then it turns out you get a distribution, and the distribution is always normal, and it's always has the correct variance sigma squared. What a wonderful result, right? So it gives you this fantastic thing. This is why the normal distribution is so important in probability and statistics and modeling. It shows up in so many different places, in so many different ways. Okay, this is this central limit theorem. A few observations you can contrast with the weak law of large numbers. If you look at the sample mean, it converges in distribution to expected value of x. And this leads to this general statement. You can make a very loose meta statement saying sum of IID random variables tends to be normal. Do I like it? I don't like it entirely because the scaling aspect is sort of hidden in that, right? The scaling is very important. If you simply scale by 1 by n, it tends to constant, right? So it's not the same as the scaling is not entirely, I mean the scaling is hidden when you say sum of IID random variable tends to be normal, okay? So you have to know in what sense the actual interpretation is. The scaling is very, very important. When you divide by root n, it goes to normal, divide by n, it goes to constant, okay? Interesting little statement about the CLT. The CLT, like I said, is a very, very celebrated result. There's lots of nice experiments. I'll let you read up a little bit on that. So there's this nice, you can build a big experimental setup and draw some marbles from the top or something, and the way it will scatter and it will form a bell curve. So this is why the bell curve shows up quite often in simulation. Statistics are very nice experiments and demonstrations you can do to illustrate how a lot of independent random variables, when you add them up with suitable scaling, you can get a normal distribution to show up. Okay, so this is a wonderful and celebrated result. Okay, so we have not seen the proof of this, and I don't think I can give you a great little proof here. So maybe somebody, okay, so this is again a post on the discourse forum. Somebody can start a post on the proof of the central limit theorem on the discourse forum, and those who are interested can participate. And the proof is strictly out of syllabus. It's not related to your exams or anything. It is just for those of you who are analytically curious about where the proof comes from. Start a post on the discourse forum. I'll also participate. Okay. So how do you use CLT to approximate probability? Now this is important for this course. Okay, so whether you understood the proof for the CLT or not, you should know how the result is to be applied when you want to approximate probability. Okay, so this is very, very crucial. Okay, so you have once again x1 through x, IID x. Okay, IID is missing here. It's IID. Let's say the mean of x is mu, sigma square is variance. I'm defining the sum, y equals x1 plus xn. So notice I'm not worrying about the the scaling and all that. I will use the scaling. I'll show you how to use it in the calculation, but people will usually just write the sum. Okay, and you'll see how the probability gets approximated. I'm interested in this question, right? This is the question we asked before when we approximated the binomial. What's the probability that y deviates from the mean mu? Y has n mu as the mean, right? Expected value of y is n mu. Okay. So what is the probability that y minus n mu is greater than delta times n mu? So delta will be some fraction. We'll pick it as 0.6, whatever. So this is the question we've asked before. So how do you use the CLT for the approximation? So it's again IID, forgot that IID here. Okay. How do you use the approximation? The crucial idea is this y minus n mu divided by root n. When I divide by root n, I'm going to get something that is approximately normal, 0 sigma squared. So in addition, I will divide by a sigma. Okay, why am I dividing by this sigma? So that I get rid of the normal 0 sigma square, my distribution becomes normal 0 1. So this is the crucial idea. So y minus n mu divided by root n sigma, I'm expecting it to be approximately normal. So any question you ask me about y, I will convert into an equivalent statement about this normal distribution, y minus n mu by root n sigma. And then find the probability in terms of the normal distribution whose CDF I know. Remember, normal 0 1, we know it's CDF, right? That CDF is known to us. It's given in tables, it's given in some computer program, whatever. Okay, that CDF is known to us. We can express the answer in terms of the CDF of the normal distribution. This is an approximation. Okay, I've put an approximation there. Nobody knows whether it's an upper bound, lower bound, whatever. It's an approximation, but it works very, very well. Okay, so the CDF of the normal 0 1 we will assume to be some f of z. This f of z is known to us. Okay, this f of z is known to us. So probability of y minus n mu greater than delta n mu, I'm going to divide both sides by root n sigma. Okay, so I'll get y minus n mu divided by root n sigma is greater than delta root n mu by sigma. Now this I will say is approximately normal, and here I should put an approximation. I'm sorry, I put equal to. This should be an approximation. This is approximately normal 0 1. Okay. So probability that a normal 0 1 random variable is greater than something is 1 minus the CDF of that same thing. Okay. So this f is known to me and I will approximate. Remember, this is approximate. It's very, very important. It's not equal or anything. So this is the way in which you use CLT for approximating probability. Okay. So notice that root n will enter the picture. It's important, and you should know which random variable we are approximating with normal 0 1. Simple, isn't it? It's very easy to use. I mean, even if you don't understand how all those limits worked out and all that, this is very, very easy to use. Okay, so let me show you a particular illustration. I'm going to approximate the binomial n comma half using the CLT. So mu and sigma are both equal to half, right? Remember, binomial so okay, so I should be careful here. So how do I get this? X1 xn is IID Bernoulli half, and for Bernoulli half these two are true. Mu is sigma is half, right? Bernoulli half is mean is half, variance is 1 by 4, right? P into 1 minus P. So sigma, this is the square root of the variance, is half. Now you remember when we discussed the weak law of large numbers, Chebyshev and all, I was interested in this event, y minus n by 2 greater than 0.6 n by 2, right? So this is the sort of probability I was looking at. Now using the CLT, I keep putting equal to here, I'm sorry for that, it should be approximate. This is approximately 1 minus f of 0.6 root n. Okay, so this f is, this just uses the formula from before, f is the CDF of normal 0, 1. Okay, so that's the formula here. And if I do 10, 50, 100, notice this. This is same as what we had before. I had the same events listed out. Probability is like 10 power minus 6, 10 power minus 10. Notice the CLT. Okay, it gives you such good approximation, very close to what you expect here in terms of the probability. Okay. So that's the nice thing to know. Approximation is really, really close, and normal approximation is a very, very good thing to do for binomial distribution. So this is how you use the CLT. Once again, not exact, approximate, not even a bound. You can't maybe prove that. Maybe in this case you can prove, but it's a little bit more general than that. Okay. So here's one more example. I've taken our other favorite distribution, y being x1 plus xn, and this x having this distribution. Okay, so here you can again see mu is 0 and sigma squared is 5 by 2. You can do this calculation. Now CLT tells me y by square root of 5n by 2 is roughly normal 0, 1. Okay, so now if I want to find probability that y is greater than delta n, okay, some calculation delta n, I've just done that. Okay. I don't know why I've done delta n, maybe, I mean it's okay, y is greater than delta n seems like a reasonable thing to calculate for this distribution. So it's the same as probability of y by root 5n by delta by 2 greater than, I have to divide both sides by root 5n by 2, right? So if I do that, I get delta times root 2n by 5, and that's approximately now 1 minus f of delta root 2n by 5. Now you can put in calculations. I hope I got this right. Yeah, sure. This should be fine. Okay, so this is the answer. Okay, so that's for that distribution. Now let's do a continuous distribution. Here I have uniform minus 1, 1. Okay, now for the uniform minus 1, 1 continuous distribution, mu is 0 and sigma square is 1 by 3. Okay, so the CLT tells me root 3 times y. Okay, remember y is the summation, is going to be roughly normal 0, 1. So supposing I want to find probability that y is greater than 0.1 root n. Why 0.1 root n, just like that, some function, right? So it's okay, some deviation. So multiply both sides by root 3 is the same as p is greater than root 3y, probability that root 3y is greater than 0.1 root 3n, and that's approximately 1 minus f of 0.1 root 3n. So if n equals 100, you know that this probability is roughly 0.2919, n equals 100, this probability is roughly 0.0416. Notice, I mean, I want you to once again appreciate how non-trivial this calculation is. Supposing you want to find the exact value for n equals 100, what do you have to do? Right? You have to find the distribution of y. How will you find the distribution of y? It's the addition of 100 independent, identical, uniform, minus 1, 1 random variables. You have to take the PDF, the individual PDF, and do what is called convolution with itself. So it's a slightly more complicated operation, and find out the actual distribution for 100 and then do an integration from 0.1 root n. Okay, so it's a lot of work. I mean, it's not so easy to do, it's not very pleasing, but notice how easily the normal approximation is giving you the formula. So clean, isn't it? And it's also illustrated in the discrete case. Look at the discrete case. In the discrete case, you have a complicated looking discrete PMF, and if you raise it to the power 100, I mean, you're going to get one big mega expression, and who's going to go in and calculate this probability? It's really, really, really hard to do the exact probability. And notice how easy the normal approximation is. I want you to take a step back and appreciate this result for that point of view. Okay, so when you have a sum of IID random variables, the normal approximation is fantastic. It gives you nice expressions. I mean, accuracy is going to be pretty good, and it works out very, very, very cleanly. Okay, much better than trying to do exact calculations. Okay, so this is a very popular method in statistics to deal with sums of independent random variables. Okay, so that's the end of this lecture. I hope you understood and appreciated how this CLT comes out of nowhere and simplifies your computations tremendously. Okay, thank you very much. I'll see you in the next lecture.